Hey, Rob.
Morning.
Morning. How was your break? Can you hear me?
Yeah, I had mine on mute. I can hear you.
Oh, gotcha. How was your break?
We had something go through here that everybody was down with a cold.
Yeah.
And then my stepdaughter got exposed, or not potentially exposed to COVID at work.
Yeah. Well, I can tell you from firsthand experience, I haven't had it, but a lot of my close family members have had it now, and there's no telling if you're gonna feel normal or like some people just don't show any symptoms. And then there's people like my wife who got pretty sick, but not like hospital sick, but probably one of the worst sicknesses she's ever had. And then,
You okay now?
yeah, she actually just got to return to school today. So she was her as of yesterday, her quarantine had finished, and she started feeling better about last Thursday or so. So she went back to school today. So the sucky part is if your daughter gets it, you'll be in quarantine from, so she'll have a smaller quarantine time than you will if you've been around her technically, because so like my quarantine won't end until the 6th of December because my quarantine doesn't start until I guess the way that when her contagious period ends, then my quarantine starts. So when they think she's going to stop being contagious from it, then the people that are around them have the 10 to 14 day quarantine from there. So I spent her quarantine time at home, and then you have to spend your quarantine time at home while she gets to leave. But yeah, it's a headache, I tell you what. So hopefully she doesn't get it.
Well, she's had 2 negative tests, but
Oh, that's good.
Can I come to the class?
Classroom? No.
No?
I notice you're in the department though.
Mm-hmm.
I know where you're at.
Okay, what happened to this camera? Why is it not zooming in? Let me disconnect and come back. Oh, I had to assign someone.
I was hoping he'd use his.
You want to tease us, Luke?
Yeah, I'm the host now, so.
I was hoping he'd use his home setup because the resolution on that camera on that board is poor.
Wait, Jordan, you mean?
Oh, yeah, sorry. Yeah, it's in the room it's a little different than it is at home for him. I think it has something to do with the upload speed, because if you look at just the different qualities in people's images, like look at Luke's image and then look at Rob's image, the difference in internet is much clearer on Rob's end. But I think that's mostly what it is. Just upload speed at the university is maybe not the best.
Actually, I tested it when I'm logged into the Edgerone.
Mm-hmm.
It's not that bad. I think I was getting at sometimes 60 to 80,
Yeah, that's pretty good.
and I don't get that at my work, but that still should be more than sufficient.
Yeah.
And
I don't know them. Not sure why it would be different. He used the same camera setup at his home and it was much better. So I'm not sure.
Oh, you're talking about what happens here?
Yeah, Robin mentioned that the quality is pretty low at the university for some reason.
I see. Well, it's one more week. Next semester, hopefully, I'll try to do something else. Come on. Okay. Oh, Rob, I have your graded midterm 3. I cannot pass it on to you. Let's see. Couple of change of plans, right? So that was homework 10. Which was due December 4, Friday. So I cannot postpone it from that point on. So what happens is that I cancel homework 10 completely, but the questions will take over into final exam. Final exam will have questions from homework 10 and additional problems. So that's a loophole in the system, right? So I cannot make anything due beyond Friday, but I can put the homework into the final exam. So is that clear? Any confusions on that? It's not that it'll be a very long exam. I only intend to put probably 2 more very related problems. So it's not that I'm going to make it very long. In this context, I should also point out that the other course, I've already put out the final. So the final exam is available for the math methods course. So similarly, this also hopefully in the next few days, I might be able to put it. So surely by Friday, I think the paper will be out, and then it will be due on, when is this due? So due on December 9, which is a, and other exam is due on Tuesday. I'll make it. Okay, officially it's due December 9, Wednesday, 4:45 p.m. But I'll accept it until December 11 evening. Okay. Again, officially this is the time, but that is because the other exam is due on Tuesday, so you get more time to spend on this. And what else? And there is a course evaluation. available on D2L? Earlier, this used to be a paper format. You used to distribute it in the class, but in the last few semesters, they are doing it on D2L. So I'll encourage you guys to fill it in. It helps out in various ways. Surely I read them. So in that sense, it's at least that much is there. And then I think the university also uses this for some statistics. So it's a good thing to fill in, but I cannot force it. So it's just that it's like it's a social social duty, I think. I would say. I'll encourage you guys to do that. Okay.
And then
Yes, Moses, you were asking a question? No. Okay, I heard something.
No.
Someone?
I do have a quick question. For any outstanding material, what day is the last day that we can?
I thought I said December 4 evening.
Okay.
Is that? I think we had sufficient time, I suppose, including the Thanksgiving break and all that. I know some of you guys, I think Jordan, it's you, like you were sick and all that. But I think, well, let's wind it up. Okay, so
December.
do whatever you can, and remember that if you're sick, I can excuse things for you guys. Like there are university rules which says that I can excuse you completely off it. So, but let's wind things up. So let me not postpone. So everything. So what is this? All. So only the homeworks, right? Homeworks due on December 4 evening. Any other questions? Did I cover everything? Yeah, okay. So since I postponed the homework, remember that last Friday I lost it. I lost a lecture in the sense I fumbled and I almost wasted the whole lecture. So I'll cover that today. And since we postponed or not postponed, I put the homework into the midterm. I'll have Friday also to use for myself. Okay, so we were talking about dielectric models. And by dielectric models, we mean what characterizes a material. And for a conductor, usually it is the Ohm's law that describes how a material behaves how the material responds to an electric field. So that's so this is Ohm's law. And more nicely, this is as a frequency dependence. This is also called Drude model. Like Ohm's law is very, we usually don't associate frequency dependence in there. The Drude model is pretty much the same thing, but we give a little structure to the conductivity. So, so the idea is that current density J of T is equal to sigma. So how do you say this? So this is minus infinity to plus infinity, dt prime, and sigma T minus T prime, and the electric field. Remember that this is in the time space And in the frequency space, it is called the conductivity. That doesn't always mean that it will be the same. It will have the same dimensions as in the frequency space. So conductivity in the frequency space has a different dimension, and conductivity in the time space has a different dimension. In the frequency space, this equation reads J omega is equal to the conductivity times the applied electric field, all of them in the frequency. So it's typically when we introduce Ohm's law in introductory physics, this is at zero frequency. When the omega is equal to zero, that means it is statics. That is pretty much equivalent to saying that the electric field is a constant. When electric field is a constant, or the voltage is linearly dependent, then you would say that Ohm's law in the static limit is valid. So what is Drude model? Drude model adds on to this. It gives an actual construction for sigma, and this frequency dependence is given as, oh, I again made the same mistake, huh? So this is epsilon naught, right? Last time I struggled with that, so this should be epsilon naught there. That's the way it is defined. So no the reason. So that's epsilon naught in here, and that defines your Drude model as gamma minus I omega. So the frequency dependence is linear in the denominator, and remember that this has to satisfy Kramer's chronic relation. So there is a real part and an imaginary part. They are connected, and you see that in your homework. Right? I think some of you have already submitted that. So those who have submitted it, you will realize that there is a real and imaginary part, and it satisfies the Kramer's chronic relation. Here, omega plasma frequency, omega p square, is the number density of the free electrons. There are two types of electrons. One are free to move around in the material, and the other are bound to the atoms. And this is the free electron, the number density of the free electrons. And this is E square over m times epsilon naught. Right? This was the epsilon naught that we were missing last time, and I fumbled a lot with that. So that's pretty much Ohm's law, and this describes how electrons that are not bound to the atom behave in a material. And the model was motivated by simply using Newton's law. We said mass of all this. So basically, to reach here, right? To reach J. So what was a strategy? So let me quickly say that. So the strategy was that J as a function of time is nothing but number density times E times the velocity of these charges. And the velocity itself is got by solving the Newton's laws for each electron. So each electron has an acceleration and it experiences a friction which is proportional to the velocity. And it also depends on how much electric field you apply to it. So that's the time dependence in here. So solve for the velocity in here, substitute it in here. That's written in this form. So it's pretty much, this is the Green's function for this differential equation. And these two equations basically give you everything in that sense. So these two descriptions lead to the Drude model. Again, this is for electrons that are free to move inside a material. But we do know that there are two types of electrons. some of them are free, and some of them are bound to the atoms. Those are, of course, extreme versions. In general, there is a whole hierarchy between them. So one is called an insulator, one is called a conductor, and you have a whole scale in between them. But now let's think of an insulator model. So that's a conductor, and now we want to talk about an insulator. For insulator, like this two relations, the idea would be that polarization.
I have a quick question.
Yes.
Is there a similar model, or how would you arrange the equations for talking about holes, like moving holes,
Oh,
opposed to free electrons, you have free holes, or
yes, yes. So let me see. We have free electrons. Yeah. So it will be pretty much the same. Let me see. What was the difference? Help me here. Okay. So.
because I guess technically the holes aren't moving, but because they're still electrons, but
Yeah, so in this model, the way we have described it, you cannot differentiate between holes and electrons, the way I have put in here. Now, what happens is that one step you can go ahead and say that all the electrons have to satisfy Pauli exclusion principle. And that brings in the feature that you have, so Pauli exclusion, so let's say this is the ground state, right? So this is your zero state. And there are negative states also in principle. But let's say if you have, if the electrons have to satisfy Pauli exclusion principle, one electron can sit in here, the next one has to sit very close to that, right? And you keep filling it, and you keep filling it. So this is the minimum, so this is called the Fermi energy, right?
mhm.
So you fill in this many states. And now the point is, for a conductor, you would say that this Fermi energy, that the electrons, so there is a Fermi energy at, I think this is the, there's a reference state, and then there are some electrons over or exceeding that. Yeah, at temperature, so increase the temperature, right? So this is at T equal to 0. So now increase the temperature, and some of them will jump out of this 0 state. So there are electrons here. But since there are electrons here, there are electrons here too, or there are holes here. And that's the idea of holes can move this way and the charges can go the other way. But the point is that the because of the Pauli exclusion principle, the friction, the gamma that we put in here, this is slightly different for these two states. So that comes out to be different. And that for that, you have to go in, invoke the Pauli exclusion principle. I don't get the.
So do you get some constant value, or
Other again?
you get some constant value that's different?
Yes, so whatever gamma is, so we have a gamma here, right? There will be a gamma, let's say this will be gamma plus and this will be a gamma minus. And these two will be related by yeah, I don't know offhand, but they will be related. How about that? Let me, that's a hint I can give you.
I think you answered my question by saying that your formulas here do not necessarily tell you the difference between a whole, and that's kind of what I was looking for.
Yeah, that is the only thing we are missing, is that we haven't taken care of the electrons spin in this scenario, and That is the main development you make when you're studying magnetism, and magnetism is all about spin. Like that's we are completely doing electrostatics here, or electricity. When you go into magnetism, the main point is that you take care of the spin, and the Pauli exclusion principle alone lets you explain lots of properties in magnetism. So, and I haven't, or we haven't done that here at all. Absolutely not. Yeah.
Would the sign of the charge come into play, since a hole would have a positive sign compared to...
No, in the sense one goes in this way and the other goes this way, right?
Okay,
A positive or a negative charge going in this direction is the same as positive going in this direction.
yeah, okay.
So it's pretty much the same. If you want, there are, yeah, in quantum mechanics, you see this whenever you put a magnetic field, there are energy levels that split into two. So that's what happens here. So there are two streams here. So it can either go this way or through the bottom, and together there is an average if you want, or another way of looking at it is that there is a symmetric state and an antisymmetric state that shows up, and new features come out of that. So that's the way to look at it. But I haven't completely done that ever, so I cannot tell you the specifics of that immediately. Yeah. And then, yeah, so the right, at least locally, I think there is a course 575 that Dr. Mazumdar teaches. And I have sat in some of the lectures at that, and he surely does that. So that's the right place to go in an immediate sense other than internet and all that. Yeah. Okay, so does that help roughly? Yeah, good point. Sometime I could incorporate that. Yeah. Okay, so yeah, so again, so conductor model is given by Ohm's law, and details are given by Drude model without the spin. That should be clarified at this point. And for an insulator, we talk about polarization, and polarization is given in terms of the susceptibility, right? So this is P of T is equal to minus infinity to plus infinity dt prime chi of T minus T prime. And again, there is an epsilon naught. And whenever I write this kind of an equation, it's understood that this is a response function, and immediately it has to satisfy Kramer's chronic relation. In the frequency space, this becomes P of omega is equal to chi of omega and epsilon naught times the electric field. Again, this could be anisotropic. I could have a dyadic in there. We are assuming that it is it's isotropic. So polarization depends on the electric field, but we would like to exactly like here, we would like to have some description of what the sigma is, what's the frequency dependence in here, and what is the frequency dependence in the chi. So that's our goal. And here the guideline was that use these two relations, right? So here now we want to talk about what can we say about the polarization. How can I read out the polarization? Here it was the current, and current density was proportional to the velocity. Polarization, what is it proportional to? Current density is proportional to velocity. Similarly, polarization would be proportional to what? Any thoughts?
Electric field.
No, that's not what I was saying. Yes, it is proportional to the electric field, but I am like, notice that I have to connect these two, right? It is built, the current density is built out of velocity. Then I give a model for velocity, which equation will give me velocity. Put that in and read out my sigma. That was the goal, right? So similarly, I have to ask, what does polarization depend on?
The dipole moment?
Dipole moment.
Dipole moment. Yes, that's correct. And dipole moment depends on position, right? Not velocity, position. Here, conductivity depends on velocity. Polarization depends on position. So it is simply Q. So again, number density, remember, right? Number density. But this time, the number density of the bound charges, since we are talking about the insulator, we have to talk about the bound charges. We are having a very simple model where atom has a lot of bound charges and there are a lot of free charges, right? So very extreme scenario. So we have forgotten all the free charges. We are only talking about bound charges. And then there are this, since we are talking about electrons, that's E and the position of each of this charge. Right? Number density times, so this is the dipole moment, right? That's your dipole moment, right? So it is number density of the dipoles. How many dipoles are there? So if you want, this is dipole moment, right? D. That's your polarization. Is that clear? So if I can solve for R, so if I can solve for the position of one atom, or sorry, one electron, then I will use this relation to identify what is my dielectric susceptibility model, at least in the time space, since this is a time relation. So that's going to be our scheme, right? So use this, but then how do I get my position? Use the same equation here, but this time it's a bound electron, right? So I have to be, so think of an electron that is bound to an atom, and you ask what are the what are the forces that will act on it. So again, use mass times acceleration. So this is the acceleration of the electron, mass of the electron of one of the bound electrons. And this will be equal to the main force that will keep it binded will be a harmonic oscillator, right? Think of a harmonic oscillator. It is going to, if you try to take it out, the force increases. So there is a natural frequency. So you say this is so minus kx, right? So this is minus k times the position. So this is what will keep it close to the atom. And just for making it more general, let's like, it's not necessary that this bound charges will not face any friction, right? It might face the same friction force also. So it is minus m gamma. So we keep that also. Velocity dependence. And of course, there is an electric field. We don't really need this because this is going to dominate. Like if there is a bound charge, the binding force is going to be more dominant than the friction force. But just for keeping this a little general, we will do this. And in fact, in this way of doing it, we have this possibility that if I set k equal to 0, I should get back the conductor model in a certain sense. So we should have a connection between this and that. So for that purpose, let's keep this friction force also. Okay, and so this will be our model. Polarization is dependent on the position, and the position will be got by solving this equation. Write it in that form and identify what is your dielectric function. So that's going to be our strategy. So again, we solve for this equation to get our sigma. So we solve the same thing in here. Yes.
About this.
Mhm.
I remember before in one of the previous lectures, you talked about that, there was no dependence in this sort of circumstance on the reference point. But what I did remember is that I thought that the dipole moment was dotted with the gradient of the electric field at the reference point.
That's correct. That's correct. So that was what was done was that we moved it in and then we moved it out again. If you follow the steps, let's go back. Which was this? You're correct. So what we did was.
I remember you said the force comes from the leading term of the dipole. And then you said something like, I don't remember.
Yeah, so the point was, I think, the point was there is a term D dotted with del, like gradient. And this was acting on, what was it acting on?
The electric field at the reference point.
Yes, electric field. And what we had to do was, I was interested in identifying the energy, right? Since I wanted to identify the energy and I was not having the magnetic field in here, so I said that since we're talking about a single atom, so this was a single atom, remember, right? So the dipole moment of a single atom doesn't depend on the position of the atom itself. A dipole moment is a property, it's like a mass.
Okay.
And then you say that, oh, this is the same as dotted with D times electric field. That's okay. But now what we are saying is that I had to pull it back outside because after you, so this was for a single atom. Like this is for one atom. When you had many atoms, what we upgraded this to, putting a number density times D dotted with del. And this number density has a position dependence. Like I could have more atoms in one region and less atoms in other region. So that brings in the position dependence. So I brought it out. So first I took it inside for some purpose. And then I brought it back outside so that I can multiply it with the P. Right? So this became your P. And then you dot it with gradient and electric field. And then you integrate by parts and get it on the other side. That is how you get that.
Okay.
That is your del dotted with P that comes in. So yes, the dipole moment of an atom itself does not depend on position, but the moment you bring in the number density, you bring in the position dependence in there, right? Because each atom could have different dipole moment. Does that make sense?
That's exactly what I was looking for. Yeah. Thank you.
Okay, cool. Okay, so okay. So again, so the strategy is that I want to solve for position here and substitute that in here. And whatever is in front of the electric field, I will read it out as my dielectric function. But we have learned something. Here what we did was that we went into the Green's function and solved it explicitly. But we already know that if I go into the Fourier space, it becomes much easier, right? It is algebraic. So why not just go into the Fourier space immediately? Don't even bother to work in the time space. So in this case, will completely work in the Fourier space. Let's begin by dividing out by mass m. So the acceleration here is second derivative of position. Right? So let me write that as dt squared, yes. And there's a velocity, so that's minus, so that becomes a plus. Okay? Plus gamma times d by dt of position, and this one is plus k over m. And let me define k over m as a characteristic frequency of the atom, which is omega naught square, right? That's what you do for a harmonic oscillator. So there is some spring associated with the atom. That's the way you can intuitively imagine that. So that's plus omega naught square. This whole thing multiplied by position r of t is equal to E over m times the electric field. So if I want to solve for this susceptibility function, this Green's function in here will be what is the susceptibility function in there. But, and this Green's function is reasonably easy to get, but we will directly go into the frequency space. Going to frequency space is easy. You simply replace d by dt with minus I omega everywhere. And switch your position dependence as time to frequency. And everywhere you do that, as far as things are linear, that is, it's not a bilinear function of the fields, you can do that. So that gives you minus I omega square plus gamma times minus I omega plus omega naught square times the position now is a frequency dependent quantity. So we have Fourier transform. So we are in the frequency space now. That's equal to E over m times electric field, which is again frequency dependent. Minus square is a plus, I square is minus. So let me rewrite this as omega naught square. Let me bring out the restoring force in the front. The friction force is minus I gamma omega, and this one is minus omega square. Or omega is equal to E over m times electric field. I am interested in the position as a function of frequency. Just divide it out, right? That's the advantage of working in frequency space, that it's all algebraic, no Green's function or no differential equation. So the position is equal to E over m over omega naught square minus I gamma omega and we almost have it in the sense that is polarization is proportional to position. Position is proportional to the electric field, and these two, if I combine them, I already almost can read it out. So if you allow me, you won't be able to see this board anymore. I'm going to go into the new board. How come we are 9 of us here? That's interesting. Are we 9? Oh, because usually there is someone or the other here in the. No, still there are 8 of us, right? How come we are 9? Oh, because the one is me. Sorry. Yeah, that's 8 people. Yeah. I don't see this computer full of 9 boxes. Yeah, sorry. I was suddenly surprised. Yeah. Okay, funny. Okay, so let's move to the new board. Okay, so again, what we have is we want to write polarization in the frequency space would be number density. Maybe I should write this first with T, right? So this is T and F E times R of T, right? This is dipole moment times number density, but these two are not time dependent. So the frequency dependence will be almost immediate. That is number density, the same number density, E times R of omega. But R of omega, we have just now derived to be E over M divided by omega naught square, I gamma omega minus omega square times the electric field. Substitute this in here, and we have P omega equal to NF. Sorry, not F, right? Why did I change that? Yeah, this is NB, right? Because we are talking about bound charges, not bound charges. So yeah, NB E square over M divided by omega naught square minus I gamma omega minus omega square times the electric field. That's almost what we want. Now we compare this with the dielectric or susceptibility definition. So polarization is the response to the electric field. So this is phi omega times epsilon naught times electric field. So whatever sits in between the electric field and the polarization as a response, that's my susceptibility, or that's the model for susceptibility in this sense. I'm just missing the epsilon naught, so I introduce the epsilon naught before I forget and mess up. And this is defined, so this whole thing will be your susceptibility, right? So we have a model for susceptibility for a dielectric material, and that is, let's call this, so this will have the dimensions of frequency square. So this will be omega b square now, divided by naught square minus I gamma omega minus omega square, where omega e square pretty much like the plasma frequency, just that this time we are, so there will be a, if you're talking about a big atom like copper, there might be a factor of 20 or something difference. Remember, anything that that's a response has to satisfy Kramer's chronic relation. So this also has to satisfy Kramer's chronic relation. And we can talk about real part of chi and imaginary part of chi, right? They have meanings associated with that. So let's see what is the real and imaginary part. For that, I will have to rationalize this. Right? So this can be written as, so multiply and divide by the complex conjugate of this. So this will be omega b square times omega naught square minus omega square. So that's the real part of this, divided by, so there is a plus I, right? So it's plus I. So the imaginary part is omega b square times, I'll be multiplying by plus I gamma omega. So this is gamma omega. I, so that's the real part, that's the imaginary part. And the denominator will be the square of this quantity, but with the complex conjugate squared. So that will be omega naught square minus omega square squared plus gamma square omega square. And here it is. If we think of this, so of course this is the real part, that's the imaginary part. What does this depend on? Even though it seems like there are how many parameters in this? Let's see. So there is omega b, right? And there is omega naught, and there is gamma. But omega naught square, always remember that whenever you have some function, this is an overall factor, I can pull that out and divide it out by chi. So this is just a scaling factor. Omega b is just going to be the amplitude of some functional dependence. So this is actually not an important factor, at least when we are talking about conductor and an insulator. So the two parameters at this stage are omega naught and the gamma. Right? Think of a damped harmonic oscillator. This term decides how much the electron is bound to the atom, and this decides how much it experiences friction. Now we can think of two scenarios, even though this is a bound model for electrons that are bound. We can always consider an extreme scenario where omega naught is negligible compared to gamma. Both have the dimensions of frequency. So we will talk about two situations. One is omega naught is very much small compared to gamma. And the other is that gamma is very much small compared to omega naught. And this we will call a conductor. But now, even though we are doing, we built a model for the bound charges, since we put in the friction in there or the gamma in there, we are able to do this. So this model is, in a sense, superior to what we had earlier, except for the fact that the scaling factor of omega b should be replaced with omega free plasma frequency, right? Either it is free charges or the bound charges. So with that idea, so let's define this to be a conductor and this to be an insulator. So this gives you a scale, right? I mean, you can actually tune them based on these two parameters, pretty much like what we have in damped harmonic oscillator, right? This is the damping factor, and this is your natural frequency of the oscillator. Okay. So how does the plot for the real part looks like? So let's see. So let's talk about insulator first. So we have an insulator. That means we have gamma is very much less than omega naught. Okay, so that dominates, and if this is small, so now let's plot real part here. So let me say, so this is the real part. This is real part of chi as a function of frequency, and I also want to plot in the same this is an insulator, so same omega, and this is imaginary part of chi. And now what happens is that at least it is clear. One thing is obvious, that at omega equal to omega naught, so we are saying omega naught is very large compared to gamma. At omega equal to omega naught, this goes to 0. So this goes to 0 somewhere here. So this is omega naught. And if that's omega naught, gamma is somewhere very small, right? So gamma is somewhere here. That's gamma. So it's very small compared to omega omega naught. But that's not what we will use the reference as. To see, so this is surely going through that point. What happens for very large frequency? Very large frequency, omega square will dominate. So that's omega square there, and in the denominator there is an omega raised to 4. Right? So there is a 1 over omega square dependence there. So it is going to go to 0. Right? So it is going to go to 0. Not only going to 0, it is going to have a negative sign also associated with that. So that's if you were or if you wonder, there might be some challenge associated with that. That's what is going to be the content of what we will talk about on Friday. But as of now, let's take it as it comes. And this is a negative number. And so if you were to plot this properly, it will be, first of all, what happens when omega is equal to 0? When omega is equal to 0, this goes to 0, that goes to 0, that goes to 0. So it's a constant, right? Omega b square, omega naught square, and there is an omega naught raised to 4. So it's some constant here, and that constant is omega b square over omega naught square. Right? So this point is a constant, not 0 at least. So overall, what happens is that it grows. It grows, then comes down, and goes like this. People say a constant thing. And it goes to 0. So I guess -1. I think it goes to 0. It goes to 0 like this. It doesn't come back up to the positive. Okay. This is symmetric. It's an even function in omega square. If I flip my frequency, nothing changes. So I can make a mirror image of this here, right? So there is a minus omega naught here. So this increases, goes down, and it goes like this. So where is my gamma? Like I told you that gamma is very small, but what's a good measure of gamma is not just that it is down here. This is actually the thickness of how much this is squeezed in here. Like this has a scale in here. That's your measure of gamma. like you might be aware of Gaussian function. Right? If you have a Gaussian function, there is a scale associated with this, right? If you have a variance, you all must be grading. And if you're graded, you want to put your scores, and then you talk about what is the variance of a distribution. So there's a scale associated with that. So that serves the purpose of gamma. Even though gamma is very small, agreed, because so that makes it fall somewhere here. But a good measure that tells you what that graph is, that gamma. And so, so for an insulator, omega naught is the frequency, how far, this is a natural frequency, and the width associated with that is your gamma. There is one funny feature that's happening here. Notice that as most of the materials are below this omega naught, so as your frequency increases, the real part of the dielectric function increases, and that means to say that the refractive index increases with respect to frequency. Unless you are very close to this material, the frequency at which the resonance for the material happens, in that case, this goes down in the sense that it is inversely related. If you increase the frequency, there's a very short regime where it will fall. So that's called, what is that called? That is the word for this. I don't remember. Extra credit. Find out what this region is called. Extra credit. I'm going to give a keyword here. How about refractive index? As a function of frequency. With that, it should immediately take you there, some article. And real part is related to refractive index. That's the main idea. When it comes to the imaginary part of chi, which is the absorption property, again we have omega naught here. Okay. And again, there is a gamma which is very small. And if we were to plot this, this time, if you notice, we have done this before, that when omega is equal to 0, then there is a finiteness. When omega is equal to 0, this is 0 right away, right? But if omega is not equal to 0, you can squeeze this in, and this is a Lorentzian. How can I motivate that? It's just, yeah, so x over x squared plus a squared. This has, so this is a classic Lorentzian. So that's what is, so this is called a Lorentzian. Like you have a Gaussian function, this is a very standard, in statistics, this is a very standard function. So that's it. Lorentzian on the imaginary part is a Lorentzian. So this immediately gives you this. And again, the width of this is here again, which is very small compared to this, how far you're from the origin, from 0 frequency. What happens on the left-hand side? So there is a minus omega naught here, right? How will it look like here? Any guesses? check and tell me, is this an odd function or an even function in frequency? If I substitute omega equal to minus omega,
It's an odd function.
it's an odd function because this is squared, that's squared, but this one is this one will make it minus. So I don't have to rethink. I just have to flip this, right? Mirror image it. So this will be like this. But absorption again, of course, is decided by these frequencies. But it is good to, it is as far as physical intuition goes, only the positive frequencies are important. It is pretty much repetitive. But what is important is that one of them is an even function and the other one will be an odd. If the real part is even, imaginary part will be odd, or the opposite. It can be either way. Okay, so that's an insulator. Now let's see what happens when it's a conductor. Right, so let's say this is conductor now. And that's omega naught is very much small compared to gamma. So gamma is very large, and we have this. So that's the real part of chi. Again, that represents refractive index, and that is a imaginary part. For chi. What we are doing is, notice how would you go from here to there? The idea is simple. You are going to stretch this gamma. Right? Imagine this figure and broaden this width of this curve and make it larger than omega naught, or make it significantly large. So that's what that's how we are going to go. And it turns out that this will be, so as you get bigger and bigger, this gets wider and wider, and these two pretty much overlap on each other on this side. So this will be equal to, there will be still a small, so this will be your that's your gamma naught or omega naught if you want. But your width is all the way here. That's it. And you want to make that very large in principle. And do the same thing here. We want to make this wider and wider, and this will stretch out here. And what will happen is that the peak here, then comes out. This, so that's your omega again. That's your. So notice what is happening for a dielectric material, for an insulator, it absorbs in a very specific region, right? Mostly around the natural frequency of the material. But on the other hand, on a conductor, it will be very wide. It will almost absorb all the frequencies. A perfect conductor will absorb pretty much all the frequencies. In the extreme limit when gamma is equal to, in the extreme limit when omega naught is equal to 0, so there is a good limit in here. So let's say when omega naught tends to 0, right? That's our Drude model. So that's Drude. And that's your homework, if you remember. And that will be actually, so this will be a real part. And in that case, so this will actually not even go to 0 at all. So this will go like this. and your imaginary part will be actually, will go all the way to infinity, and it will be like this. It crisscrosses. So that gives and this whole thing together, so this model is called Drude-Lorentz model. It's often also called the Fermi model. Or it's better to say that in high energy physics, it's called Fermi model, but most of the places this is called Drude-Lorentz model. Okay, that's all good, but let's clarify one thing right away here, that when the frequency is very large, right? If the frequency is very large, this dominates, this term dominates, and that's with a negative sign, so I can drop these two quantities, and chi becomes a negative number in that case. Right? What does it mean to say that chi is negative? So can susceptibility be negative? And what would it imply? Right? So let's investigate that, and we'll come back to that, the discussion on Friday with that. So let's quickly talk about what happens when chi is, so notice when omega is very large, omega is very much larger than omega naught, and gamma, your chi apparently is equal to omega b square or omega p square over omega square. Right? There's a minus sign. Chi, remember, was epsilon over epsilon naught minus 1. So this is, yeah, that's. So that means your epsilon over epsilon naught is equal to 1 minus, clearly this is less than 1, right? What is the implication of the dielectric function being less than 1? What would it imply? Any immediate thoughts?
That it's not a dielectric?
No, there's a much more serious issue there. No, not about dielectric.
Well, light would travel faster.
Yeah, that's very good. And that's a very good point. So if this goes less than 1, light would go faster than light, or it would go faster than speed of light in vacuum. So let's see that. Why is that the case? Remember here, so let's go back a little bit. There was an energy flux, right? Pointing vector, if you remember. Pointing vector. So how can I motivate this? That's fine. There are many ways of motivating it, but one, since we have done this pointing vector, which is energy flux, right? So that's flux of energy. Is equal to S. Right? We call it S. And I'm just going to naively argue, this is a wrong argument, but this is how you encounter a paradox kind of thing, but we'll settle this. Right? So S was equal to E crossed with H. And we also had flux of, momentum density, right? Electromagnetic momentum density. So this was energy density. So momentum density was equal to G, which is equal to D crossed with B. If you're in vacuum, it is easy. You would say G is equal to epsilon naught times E crossed with mu naught times H. And you would say, oh, epsilon naught and mu naught, that's good. So this is equal to epsilon naught mu naught times S. And that's equal to 1 over C squared times S. That's good, right? So that's, so whatever comes in this denominator here is the speed of light in that medium, right? In this case, it is the vacuum. So C squared is a measure of the speed of light. Again, this can be done in various ways. You can write the wave equation and identify that. That's another way of doing it. But using this as our mode, now let's say that we are in a material, right? So we are in a uniform material where the whole space is filled with that dielectric material, and we have G then is equal to epsilon times mu times E crossed with H again, right? Same idea. And now I want to again pull out things. So I will say this is epsilon over epsilon naught, and this is mu over mu naught, and this is epsilon naught mu naught times E crossed with H. Now it turns out that, I think I should have mentioned it here, the refractive index of a material is defined as epsilon over epsilon naught times mu over mu naught. So that's a square of it. So this is the square root of it. And refractive index is always greater than 1. Right? So again, I didn't actually do too much because here I said, oh, that should be less than 1. So I'm kind of calling that property again, that refractive index is greater than 1. So if you use that as your definition, then this is m squared over c squared times s. So, so your c prime, so the new speed of light in this medium is c over n. You're good if n is greater than 1. Right? So, or let us say that I don't even put this restriction, right? That's a refractive index. If I have n greater than 1, I'm good. Then speed of light in the medium is less than the speed of light in vacuum. But if n is less than 1, which is what we have here, right? This is n is less than 1, then it seems like you go faster than speed of light in vacuum, right? And that's not convenient because that conflicts with Einstein's relativity. Right? So we'll come back and we will say that. So what is the catch in here is that when we say that the whole space is filled with a medium of constant epsilon, that's unrealistic. Remember, there is frequency dependency in here, right? We have to talk about the frequency dependence, and we will see that if you do this carefully, this is not less greater than c, this will be smaller than c. So this was done by Brillouin. So this was a sort of a Brillouin, L-O-U-I-N. This was a paradox right after relativity, and it was Brillouin who settled it in 1914. Remember, relativity came in 1905, and this was not a convenient thing to have around. But it took some time, but Berlin solved it. It's not the most easy way of seeing it, so we will actually have to talk about material properties and so on. So, but we'll see that how we can settle. So that's what we will do on Friday, and we'll stop with that. Okay. Any questions? That's all. It's nice to see 9 boxes filled here. I think Avinash is the one who's never there. Avinash and Rob, right? Usually.
I wanted to come to class today and you said no.
No. I think we'll get in trouble. Yeah. Remember, I already got in trouble for moving tables in the first part of the semester. So I'm already flagged, right?
If it's any consolation, I get in trouble all the time at my job.
Yeah.
But you are a tenured faculty, right? So nobody can fire you.
I'm not tenured. I'm not tenured.
I was talking to Rob.
Oh, Rob, yeah. Yeah, he's safer. Yeah.
Well, thank you.
Yeah, thank you. And so we'll see you. Oh, tomorrow I'll see most of you guys except Rob, I think, tomorrow again.
Not me.
Oh, yeah, Rob and Avinash. Yeah.
That's okay. Avinash and I will be in another class this afternoon.
Yeah, I'll see you there.
What class do you have this afternoon?
Solid state physics.
Ah. Good.
So, everybody stay safe.
Yeah.
Oh, I wanted to ask a question regarding for TAs with labs. I haven't done the last, like, is the everything being due at the end of this week? Does that hold for all classes?
Oh, is this to me? Are you
Oh,
addressing?
I'm asking everyone because I haven't done the last round of labs yet for my A lab, and I was thinking of maybe.
Usually you will get an email from, what's his name?
Scott.
He literally just sent an email. Yeah.
Yeah.
Okay.
Usually they'll send an email in the last week and tell you when all of your grades need to be in by. And then once they're submitted, you don't do any submissions, but I guess the overall lab instructor, I can't remember his name for some reason. Tori, yeah. Usually he'll also send an email telling you when everything needs to be in by, but you probably should get it this week for sure at some point. But I think I remember it being due like the Sunday, like would be this Sunday, I think, because finals is next week. It actually may be next week. Don't take my word for it. It may actually be next week. Because I think the grades are due the week after finals week.
Are they supposed to be doing an online lab this week?
Yes, and that was kind of my question. Was like if everything has to be in by the end of this week, I mean that's kind of tight. So
if I don't get anything by today, then my students are going to be. I'm just going to drop it because.
Well, that's what I was thinking too. Scott just sent out the files. Like
I haven't even gotten that yet.
Yeah, I mean it was literally like 2 minutes ago. But yeah, I don't know. It's kind of tight. I'm kind of thinking about just dropping those. I just wanted to consult with you guys.
Yeah, I think any decision you make in terms of dropping is probably the right decision. If it feels like it's a super crunch for students, especially, not so much for you, but for students, then I don't think anybody would have a problem with that.
Yeah.
Yeah, most probably there is a rule in a normal semester that you cannot make any homework due beyond Friday
Mhm.
of the last week of classes. It's generally there, and I kind of stick to it. And especially if it is an introductory physics course, they have all the reason to complain, right? If you give them a loophole, and they will try to complain. So it's good to not do it, but if necessary, of course, make it a midterm or make it a final. Make it part of your final.
Well, that would be, since it's a lab course, there's no,
Right.
Oh, there's no final, I see.
yeah.
We have finals paper. Come on, man.
In your lab?
Yeah.
Hmm.
I think it has to be written in the syllabus. Yeah, it has to
It
be
is written in the syllabus. Yeah.
Yeah, then it is okay.
Yeah, I think that's more, maybe that's more of an upper level, you know,
Come on. It's 200 level physiology.
physiology. Oh, okay, I don't know.
Your favorite class?
Then.
Come on. It's not my favorite. I hate that class.
I know.
Well, it's not like I'm struggling with that class. I am mostly, I guess, like hundreds in exam, but it just requires a lot of work.
It's the busy work.
Yeah.
So Jordan, have you got back to normal, or how does it? Are you still quarantined?
Yeah, I have to quarantine until the 6th. So my wife, her quarantine ended yesterday, and I think it was Thursday of last week. She started feeling a lot better, not really feeling sick anymore. She still can't smell or taste anything, which is kind of weird.
Weird.
But yeah, she was able to go back to teaching today. But like I was telling Rob at the beginning of the course, so I never really got sick. I just kind of took care of her. But people that are around people that have COVID actually get quarantined for longer than the COVID people, because your quarantine as someone who's around someone with COVID doesn't begin until this
10th day or something. Right?
till
Seven.
yeah, their symptoms kind of end. So because that's their contagious period. So you're exposed during a contagious period where she can't really get it again for some time.
But then, just for argument's sake, one can use the second order effect and say that if you were sick and she gets sick because of you again, so she can also be. So in principle, both of you should be simultaneously.
As far as what I've seen, for the most part, people, it's kind of like chicken pox.
Yeah, does it come
you
out?
can- Yes, you could potentially get it again, but it's a very rare case where you would get chicken pox again. So
Yeah.
It is just for
Theoretically,
argument.
she could still be carrying it though. Like if you had it and you were contagious, then
No, the thing is, if both of you have the same strain, then she's not gonna catch it because your body already knows, hey, it's something that we need to kill,
yeah,
and
she
the
should-
body
she should
already has
get a contagious-
antibodies. But if it has a different strain, then it might take some time to build antibodies.
Well, if I ended up catching it with a different strain than my wife, that's a miracle.
that would be pretty surprising. Yeah.
I got through 4 weeks sitting at home with her having it, and yeah, it's a big mess. I tell you what, it was pretty crazy. She got pretty sick. I mean,
And you didn't get sick at all, right?
I got sick of staying at home, and I got sick of like hand over foot taking care of my wife.
So you're the secret. They need to look into your body to see what's the secret.
Yeah.
I
Well,
think-
apparently, my quarantine period is the period of which I could still start to show symptoms and get sick. So on December 6th, that's the 14-day mark from when her contagious time should end. So if I don't get sick by then, I'm probably going to go get the antibodies test done. That'll tell you if like, hey, you had it, you just never showed any symptoms. So,
Good.
but her entire high school is like all the teachers are getting it.
Oh,
So
no.
yeah, it's pretty bad.
Oh,
But
Yeah.
they won't shut down because they need money. So they just bring in subs they can't really teach. So there's a bunch of subs they can't really teach. All the teachers are out. And like half the school has been quarantined at different times. And if, you know, like some kids have been quarantined for like 2 to 3 months, because if you're within 6 foot of a kid, even if you don't show any symptoms or signs, if you're in that region at any point, say like in class, or if you're in gym class and you're playing basketball or something. So some students have been out for like 2 straight months because they come back to school and then they're around somebody again who tests positive. And then anybody that was within that 6 foot range for the past however long the contagious period would have been for him to contract it. Hundreds of kids, again, you know, just are gone from school. So, and it puts a lot of stress on the teachers, because the teachers have to then teach almost 2 different courses at once. They have to come up with like an online, which isn't a typical thing. So they teach their normal, you know, in-class stuff. But that doesn't really translate for high school students. They can't just like do what we're doing here. So they have to implement some other facet to teach students that are at home. So they're doing online teaching and they're doing in-class teaching. So they're like wanting to pull their hair out. And they've come up with this term that's called toxic positivity, I think is the term they've come up with, where the leaders of the school who are keeping them in school send them messages all the time like, we're so proud of you guys. Thanks for being so strong through this time. But they don't really do anything to help them out. Like, they're being very positive, but it feels kind of toxic. Because like, why would you send someone, hey, hang in there, you're doing great, but not really try to help them in any way or facet with the problem? And so there's a lot of unhappy teachers, I think, at their school right now. So it's a mess. My life, my wife's life has been crazy for the past 2 months, and just trying to hang in there basically. But I see the end of the tunnel. Hopefully I test positive for the antibodies when I take the test. And then next semester, I don't have to worry about anything. I can just go to the university. I will. I won't have to worry about any of that sort of stuff. So that's a positive outlook, is that my next semester should be much better than this one. So anyways.
Michael, have you caught up?
I'm getting there.
Okay.
I'm getting pretty close, actually.
Good. Okay. Okay.
Thank you.
You guys can hang on if you want. You want to hang out?
No, I need to work on catching up still. I have a few more. I'm almost all the way caught up in math methods, and now I've started my catch-up process in this course. So yeah, it's
Good.
a lot.
Good.
Thank you.
Take care, everybody.
Yep.
Yeah.
Stay safe.
Thanks. Thank you. Enjoy, guys.
Bye.